My talk is going to be about PD simulations on general unstructured grids. So you can use that, of course, for macro and mesoscale modeling for materials. But this is really a general talk about how finite elements can allow you to discretize a wide variety of physics. I am focusing on unstructured grids. Of course, you can also use structured grids for different types of applications. But this is the type of problems that arise in many industrial and lab and computational science applications, and that's the focus of our work. I'm Tzanio Kolev from Lawrence Livermore National Lab. This represents, of course, the work of many people on these projects. I'm going to tell you a little bit about them, the MFEM, BLAST, and SEED projects. And I'm going to start with why finite elements. There are many ways to discretize problems and PDEs on unstructured grids. But mathematically, I argue, finite elements are the most beautiful ones. Because the theory is just functional analysis applied at discrete level. So it's the strongest one. It gives you a lot of rigor and prediction and confidence in your simulations. There is no tricks in them. You can run on general unstructured grids. You don't assume any structure in the problem, curved grids. And when it comes to different physics, they have this de Rham cohomology that connects in a very natural way all the spaces that you need for different physics phenomena. So for example, this space H grad is the degrees of freedom in that space associated with the nodes, the vertices of the mesh. These are kinematic variables like velocity, position. The space L2 consists of discontinuous fields on the elements. That's very natural for thermodynamic quantities like pressure, density. And then these two spaces, H curl and H div, these are spaces of vector fields with partial continuity of tangential and normal component. They're very natural choices for electromagnetic phenomena and for example, flux-based radiation diffusion. With finite elements, you can take this continuous de Rham complex and fully represent it on a discrete level, including all the differential operators between them. Okay, so finite elements have been around for a long time, but recently, how the finite elements have become extremely interesting. And that's partially because they're no longer expensive. They used to be very expensive, but with GPUs, flops are free. And so these additional flops that before just gave you better result, now also allow you to get better result, sometimes even faster, to utilize machines better. And not just for smooth problems, as it was well known for a long time, but also for problems with choke. This is one example here. This is a compressible flow where higher the elements and higher the grids allow you to push this problem much further than you can with traditional methods. So I don't know if you can see very clearly, but from here to here, this is one computational element. You can actually have the mesh follow the flow in ways that you simply can't with linear elements. This mesh will tangle right away, and it will be a catastrophic failure of the computation. With higher order methods, one thing you can do is you can bridge structured and unstructured grids. Because generally the grid is unstructured, but inside each element, for example, on a quadrilateral or hexahedral mesh, you have a perfectly structured lattice of points. Similarly, you bridge sparse and dense linear algebra. Globally, the problem is sparse, but inside each element, you actually have dense linear algebra that is perfect, for example, for GPUs. That's what they're optimized for in terms of machine learning. And then you have the order, which is a performance tuning parameter that allows you, by increasing it, to dial up the arithmetic intensity, which is so adjust to different machines. That is very important in the landscape that we have in HPC where hardware is changing dramatically. So this is another example. This was a compressible flow. This is an example of an electromagnetic simulation of propagation of core edge tokamak electromagnetic wave propagation for fusion, tokamak fusion. This is not free. It comes at the cost of having to do new and interesting math, which is also a plus in my book. But you have to be very careful because great power, great responsibility. Higher the finite elements have a lot of, they can express a lot, but they can also get out of control very easily. Gibbs phenomena and things like that. All right, so I'm going to focus on talking about MFEM, which is our library for finite element methods at Livermore. But I should say upfront that there are many other alternatives. There's This is a mature field. There's a lot of mature software libraries that you should use instead of writing finite element library from scratch, unless you want to learn. And so some other options are Due2, Phoenix, Firedrake, and Moose, and there are more. Now, we developed MFEM because we wanted a combination of features that we just couldn't find in other libraries. We wanted very flexible discretization that support both simplex, so triangular and tetrahedral elements, as well as tensor product elements, quads and hexes. We wanted to experiment with a lot of different discretization methods like DG, hybridized DG, DPG, isogeometric analysis. Adaptive mesh refinement was very important for us, and so we wanted both conforming refinement on simplex meshes and non-conforming refinement on meshes that are tensor product elements. We wanted arbitrary order spaces on arbitrary order meshes, so that is important for us. And we wanted to scale. We have these big supercomputers at Livermore. We wanted to scale to millions of cores. We wanted to run on GPUs, and that's what MFEM does today. We also integrated with a lot of other mathematical libraries for solvers, for time integration, like Hyper, sundials. We have very strong connection to Hyper, and so in particular, we have very performant solvers and preconditioners. I'm going to talk about this a little bit. And this is all open source and freely available. And part of a lot of projects and meta projects like XSDK, but in particular, the Exascale computing project and the SID Co-Design Center. And I'm going to mention about a little bit more about that later. Okay, so just to give you an example of what this means in code, and you can play with this more tomorrow if you want. In finite elements, we need to discretize geometry, the mesh. We need to discretize the spaces, the fields. Well, I'm not expecting you to read that, by the way. I'm going to zoom in. Then you have to find linear and bilinear form. This is the right and left-hand side. You need to form a linear system that you solve, and then you get a solution, and maybe you can visualize it. And this is pretty much it. In MFEM, this is 100 lines of code that works for any order, any space, any dimensions with no external dependencies. You can download and build this in 5 minutes and run it on your laptop. Most of this code actually is comment. The mesh is just, this is a C++ code, so you create a mesh object of class mesh, you read it from a file, and then you refine it a few times. The finite element space is done for something called finite element collection that expresses, for example, in this case, that we have a nodal finite element space, H1. The previous slide, it was called also HGRAD. That's another name for it. And so you put together the mesh and this H1. You can specify the order of it. It's, again, runtime parameter and define a space. This is the right-hand side. It's a linear form that's an integral of a basis function against a given coefficient, a continuous function, in this case, just one. The fields are, the finite element fields are called grid functions, and this is our known field. The left-hand side is a bilinear form. It's an integral. In this case, diffusion integrator means grad U, grad V, where U and V are different basis functions. We eliminate boundary conditions. We extract the matrix, and we put this A, B, and X together in a linear system that we solve with preconditioned conjugate gradient, and then this is the visualization. So it's really just a few lines of code. Now, one of the things, so we wanted to experiment with MFEM and do a lot of things like this on our laptops. But then we also wanted, with very little changes, to run on the supercomputers. And one of the things that MFEM makes very easy is to turn this simple serial code into a high-performant, highly scalable parallel code. The only differences are that now you have a parallel mesh. So the mesh is split into components. Each component lives on its own MPI rank. The finite element space also has to be split. And so now you have degrees of freedom that are shared between multiple processors. There's an interpolation operator that maps the unique degrees of freedom to all degrees of freedom. So these degrees of freedom, the input is not shared, but the output is shared, so you duplicate values. And we call this P. Everything else, you just basically put parallel in front of the name. So you have grid functions, linear and bilinear form that are now par grid function, par linear form, par bilinear form. And what happens is you assemble the problem independently on each piece, and then you tie them together with this operator P. You do variational restriction P transpose AP. That basically assembles the contribution of shared degrees of freedom to form a global problem. And then now you have a global linear system that is hard, so you use something like algebraic multigrid to solve it. And then you can visualize it the same way. You can see the independent solutions on different MPI ranks. Okay, so this is, I don't know, maybe 20, 30 lines of changes that are mostly trivial. Now it uses hyper for very scalable solve, and it can run on tens of thousands, hundreds of thousands of MPI ranks with very small amount of changes. And now we depend on hyper and met is just for the graph partitioner. And I just wanted to show that, most of it. This is this P transpose AP operation. It's a one line of code here, and this is the calling. This is one line of code to call the hyper Boomer AMG algebraic multigrid preconditioner for the problem. All right, so this was just example one. There are many examples in MFEM. I think more than 40 in the last count that range from electromagnetics to subsurface flow to many other fields. And they're part of this ecosystem that fits into the SEED project and its applications. SEED is part of one of the co-design centers in the Exascale computing project. That then fits into the global ECP application space. These examples are very easy initial steps that you can start from if you want to build your own application. And they show a lot of the integrations with some of the packages we have. Now, on top of the examples, then we have mini apps and real applications. These are just some of the examples of real-world applications where MFEM is used. Inertial confinement fusion, this is relevant to the recent fusion result in NIF, the National Ignition Facility at Livermore. Topology optimization for additive manufacturing. I mentioned tokamak fusion. We have a lot of folks from, say, healthcare fields like MRI modeling and heart modeling. And this is another MHD example from, again, related to tokamak fusion. So let me give you very brief, just a little bit of details on this application, the BLAST code. BLAST solves the compressible gas dynamic equations in so-called L formulation, where we have a Lagrangian and advection step that alternate. In the Lagrange step, we solve a system of conservation laws for mass, momentum, energy, and the mesh moves. So there is dx dt equals v is the mesh moves with the physical velocity. This is an example of this evolution, and this is part of what I showed you in the beginning, the example of this very swirled mesh. Here we just use a classical Galerkin-Howard finite element methods. Then there is a stage where we say that this mesh is too curved. We want to improve it. And when we do that, we also need to transfer the field from here to here. This phase is called remap. This is done in advection formulation with discontinuous Galerkin, where we solve, again, DG, discontinuous Galerkin equations for momentum, mass, and energy. And here we use this Bernstein basis, which is a special Howard basis that allows us to control the functions. Positive functions have positive degrees of freedom. All right, so this code has been, this is an MFEM-based code that uses a lot of its features, like Howard meshes, for example. And it's been used for a lot of things. These are some of the examples of large-scale simulations of relay Taylor instability. So this is heavy over light fluid that mix. This is a 3D version of that. This is called a triple point shock, this swirling problem. Implosion, this is very similar to the NIF capsule. And preservation of symmetry. So this is if you have a spherical shock wave on a mesh that is not spherical, you expect to preserve symmetry. And how the methods are really good for that. So things like, we don't usually have error estimates for symmetry preservation in finite elements. So that's not a quantity that's directly measured by the theory, but empirically, how the geometry in particular really helps with symmetry preservation. Okay, so this was performance in terms of quality of the results. This is performance in terms of HPC utilization. So this is a strong scaling of this full L code. Different curves correspond to different orders, and if we go to high enough order, this is order 16 here, you can scale perfectly strong scale down to 1 element per core. And this was on the BGQ machine, so this is quite a few years now, 130,000 degrees of free, 130,000 MPI ranks. So quite a bit. This plot is a bit different. This is, here we're doing P-refinement, which means we're increasing the order on the same mesh. Here, when we are increasing the order, we're also coarsening the mesh. And so the number of degrees of freedom remains the same. And as you can see, different orders actually are on top of each other. In fact, we have better results now where high orders are faster for the same degrees of freedom. And the intersection point with classical methods is just at 256 cores, which at the scale today's supercomputers is not a lot. Okay, so I want to now go back and dive into some of the foundational algorithms in finite elements and tell you a little bit more about recent progress and how they're implemented behind the scenes. And I'm going to start with adaptive mesh refinement. Okay, so I mentioned this. There are two flavors of adaptive mesh refinement. Conforming one, that is natural for meshes with simplices. A non-conforming one, where you have degrees of freedom that are not real degrees of freedom. They should be constrained. That is natural for meshes with quadrilateral hexahedral elements. In MFEM, we support both. We want to be general, so we support both simplex and tensor product meshes. When we, it's not a full HP refinement, if you're familiar with that term. It's H refinement with a fixed P, so we refine the mesh for a fixed polynomial order. But other than that, everything is really general. So we support all the spaces, 2D, 3D. There's no restriction in the non-conforming case on the number of hanging nodes. So we can refine one side a lot. It doesn't have to be 2 to 1. We support anisotropic refinement, which means refining only in certain directions. The refinement in serial and parallel. And the most important thing probably is that it's independent of the physics. This is just a different finite element space. It's done at the finite element level. Okay, and these are just two of the examples in MFEM that show that. Now, how is it done? If you have a coarse and finite element like that, you restrict the fine degrees of freedom to be the interpolation of the coarse degrees of freedom. And so that's another interpolation operator. Let's call it Q here. And you do that phase by phase, accounting for the fact that you may have, like in this case, a degree of freedom that is a primal one from this relationship, but from this relationship has to be constrained. And so these constraints propagate. Essentially, you're multiplying these constrained matrices, these local constraint matrices. This is for degrees of freedom that are vertex-based. You can also do it for degrees of freedom in these spaces, H curl, for example, where they're associated with edges. And so in this case, for example, this degree of freedom is a half of the coarse one. And so you collect all these local constraints, and you form a global matrix P that takes the true MR degrees of freedom and interpolates them to all the constraint values. This is actually very similar, in fact, the same matrix as the P that we used for parallel assembly. And the way we form the global MR problem is also the same. It's P transpose AP. And all this is saying is that we're solving the original problem in a subspace that is the range of P. So we're imposing the constraints that we're in the range of P that we're conforming. Okay? The advantage of this is that locally you assemble on each element, you can solve the same problems as before. You don't need to change your code. Anything you could be able to solve before, you still can solve. You just use a different P. Okay, so this matrix A does not change. You don't need to know about AMR when you do your local physics. Okay, so just an example. This is a random refinement. You can really see it's a random refinement. And you define this P operator, and enforcing conformity, you get a continuous solution. This was just a stress test. Here's a more interesting example where we actually do intentional anisotropic refinement aligning to a shock in 2D and 3D. This is, I think, the 2D case. And you compare two sets of curves. The dashed ones are just with regular uniform refinement, and the solid ones are with the anisotropic refinement. And as you can see, first of all, higher order elements really help. So H refinement with a fixed P actually is, if you do the HP curve, it's going to be something like this. So in this plot, it's quite okay. And the second thing you see, the anisotropic refinement. For problems like this, where you do want to align really to something that doesn't fit on the geometry of the mesh, anisotropic refinement is very useful. And that's one of the main features of our algorithm. Okay, this is another example. This is preservation of symmetry for radial shock with random refinement. We can do it quite well, including in parallel on 4,000 cores. And this is how it works dynamically in practice with refinement, derefinement. This is the parallel decomposition. We use a space filling curve for that. This is 16 cores. But as you can see, as the shock progresses, we refine in front of the shocks, we derefine behind it, and we decompose the problem so we're always almost perfectly balanced, plus or minus one element. Okay, these are the actual scaling results for that on 4,000 MPI ranks. 384,000, sorry, approximately 400,000. And this is one of those plots where you have a strong and weak scaling on the same plot. So the solid lines are strong scaling, but if you maybe you can't see the dashed lines, there are dashed lines connecting these guys. They correspond to weak scaling. And as you can see, for large problems, we strong scale quite well, but even for small problems, the strong scaling is pretty reasonable. The weak scaling is great. And this is just testing the AMR capability. This is not testing any solve. There is no physics here. This is just refinement, assembling the problem, error estimation, refinement, and so on. All right, I do want to emphasize again, this is in the finite element library. This is not in all applications. Every application that is based on MFEM automatically gets this for free. And there are other solutions, P4S, TAMREX, but I think people shouldn't reinvent AMR in all of the codes. Now, another algorithm that has to do with meshing is mesh optimization. So AMR is H refinement. This is R refinement. Mesh optimization means that you just move the nodes and you try to improve the quality of the mesh or to adapt to certain feature that you want. So this is an example of a higher the mesh optimization. And when you do that, just like in remap, you also have to interpolate from the old to the new mesh, from the old to the optimized mesh. And this is shown here. You have the same function. The mesh flows through it. You want to preserve it. And this is a discontinuous function that's not aligned with the mesh. So you may not actually see it, but it's a higher order function that changes. And the fact that it's higher order allows us to capture this variation inside the element. OK, so for that, one way to do it for harder meshes is for a project we have in the Office of Science called Ethos, where you describe the mesh geometry just as another finite element field. Okay? The topology of the mesh is given just in terms of its vertices, what connects to what, but the geometry is described in terms of nodes, which are another finite element function. And for that finite element function, you have a Jacobian A, and basis functions W, and so forth. There are many papers in this field, and Mark Shepard's group, Suzanne Schoens, and folks in Europe, and this is our approach. It's an extension of what's called the target matrix optimization paradigm, where at each point you have a function mu, pointwise function that tells you what do you consider good quality, what is the measure of quality in terms of the Jacobian T, It's not a direct Jacobian from the reference to the active element. It goes for this target element, and this target element allows you to be very precise. Maybe you want a squished element, or maybe you want a rotated element. This quality metric now can control independently things like shape, size, orientation, but it's just at a point. To get the full minimization problem, you integrate it over all the elements, you form a global problem, and so you control the quality locally, but you optimize globally. That's important to get over corner cases of global influence. And so you do that with Newton, you compute the metrics. This is all finite elements. So all this optimization can take advantage of the finite element machinery, GPU, matrix partial assembly, and so forth. And in applications, I don't know if you can see this, you can align, you can use it, for example, to align to specific features like this swirl here, this kind of like a material interface. You can use it to define geometry. You can kind of use it as a mesh generator. This is an STL file, and we're defining a mesh that's mapped to it, while preserving quality. You can use it to maintain very fine resolution in this shock problem. That's a kind of ball hitting a wall. You can combine it with H adaptivity or working on HR adaptivity. And it has to be coupled with this discrete field transfer. And in MFEM, we have at least two ways to do that. One is advection PDE based, which is appropriate for problems where the mesh has the same topology but different positions. This is essentially solving DG advection, so the kind of the dual of DG advection. Instead of fixing the mesh and moving the function, here we're fixing the function and moving the mesh. And the other is Howard interpolation. So this is conservative. It has a lot of very nice property, except for monotonicity and positivity preservation. That you have to always work on that. This one is not conservative, but it's very general because it just evaluates. It's a very efficient way to evaluate the finite element field into a point cloud that is not aligned with quadrature points. And that basically gives you the degrees of freedom from one mesh to another. And this was something we worked on as part of the ECP. Okay, so this is meshing. I want to talk about scalability. So these two simulations here, the first one is the triple point, and the second one is the Relay-Taylor instability. And they're kind of early. They're not maybe very impressive. Doesn't look as cool as the other triple point. But they are impressive in a way because they're done just on 2 elements here, or 4 elements here. This is what an element, a Howard element, could look like. This is what a Howard function on a Howard element could look like. You can almost reproduce here a step function on 2 elements. In this case, elements of order 11 and functions of order 12. But you can see that if you have to deal with something like that, if you want to really propagate physics inside the element, you cannot make decisions at an element level. You cannot say this is the element size. Size has to be defined pointwise at the quadrature point level. Right? You cannot say this is the viscosity I'm going to use in this element. It needs to be defined pointwise too. So there is a lot of very delicate changes to physics algorithm that need to happen. That's one. The second thing is, again, related to HPC. Everything, all degrees of freedom in this element are fully coupled. And so it becomes extremely expensive. It's very easy to have algorithms that are O of p to the 9th, where p is the order. When p is 10, that's 1 billion flops at an element. You cannot afford that. So the other thing is that you have to be very efficient. And improving application algorithms and efficiency of Howard methods have been the focus of this seed co-design center. And that's the big project in part of the ECP, the Exascale computing project that we've been working on for 7 years now. It's been a lot of fun. It's coming to an end, unfortunately. But it involved more than 30 people, 2 labs, Livermore, Argonne, and 5 universities. And the focus really was how are the spectral elements, generally PD discretizations on unstructured grids, but making sure they work well on future hardware and making sure that the algorithms are performant and robust in ECP applications. MFEM was a major part of that. I led this co-design center, and NEC 5000 was another major part of that. That's an incompressible flow solver from Argonne National Lab. All right, so these are some of the applications that we targeted as part of the ECP. Compressible flow is the application I discussed, but also climate, exawind is wind modeling, nuclear reactor modeling, additive manufacturing, fusion, combustion, and more. We're always interested in working with new applications, by the way. So if any of this is interesting and you want to work with us, please let us know. And I'm gonna go straight to the math. This is basically the mathematical foundation of everything we did in SEED. It's understanding what a finite element operator really is. Picking it apart, decomposing it in this series of variational restrictions with an operator P, G, B, and D. And when you do that, you expose several levels of parallelism that are critical in the implementation. So P is this operator. We've already talked about it. This is the true degrees of freedom, the unique degrees of freedom that you're solving for. Interpolate from them to degrees of freedom on each MPI rank. After you apply P, you forget that you're in parallel. Okay? This is all the parallelism in the problem. It's all in P. If you have adaptive mesh refinement, P also includes the interpolation weights. G takes the local problem, the local mesh you have now on each MPI rank, and interpolates data on each element. After you apply G, you forget that your elements are part of a global mesh. Now you have independent data on each element. Then B takes the data on each element and transfers the degrees of freedom to quadrature points. At this point, you're completely embarrassingly parallel. Each quadrature point is on its own. And that's where this operator D is. At each quadrature point, it maps quadrature point to quadrature point. You apply all the physics there. So for example, coefficient, equations of state, material models. It all happens completely independently. The geometry, all the Jacobians, they're all at quadrature points. Okay? So this is essentially the physics, if you want to call it that. This is at this Q vector level. And then you go and assemble back with B transpose, G transpose, P transpose. So if this is the scattering, this is the gathering to form the global operator. So if you want to apply this operator, you go and you do a round trip here. And now the only question here is, what do you assemble and store, and what do you apply on the fly? If you assemble and store everything, it's a global matrix. You never want to do that for a higher order discretization. Even for a low order one, maybe it depends on the definition of low order. Oops, sorry. You can assemble things at this level, you can assemble at element level, but really what we are advocating is what we call partial assembly, where you only assemble and store data at quadrature points. Everything else is evaluated on the fly. And that is critical because in terms of memory, that's optimal. That's all of one storage per degree of freedom. And memory transfer is the killer on these new machines. That's what you want. You don't want to actually flops are not that big of a deal, but memory transfers are. If you have a global matrix, it's all of P to the D per degree of freedom storage. If P is 10, that's 1,000 times more. So there is a very big difference here and very big advantage to store a higher order operator in this factored form. It's the natural format for it, as opposed to a global sparse matrix, as we're used to for lower order methods. Okay? Now this was, I don't know why this changed, but this was the motivation for a new library we started on the SEED project, libseed, that basically takes these pieces and applies the operator for you. It's kind of like a BLAS, like BLAS and LAPACK applies dense matrices, but this is for sparse higher order matrices. And another advantage of this is that this allows you not just to optimize things when you implement them, but it allows you, for example, to differentiate this operator to obtain Jacobians. When you differentiate this, all the derivatives go into D. And so instead of performing one big automatic differentiation, you perform a lot of small ones independent of each quadrature point. And we have a new project together with this library called Enzyme and MFEM to do that in a very user-friendly way. So from the same representation, you get both performance and Jacobians. All right. Let me see. This is just an example of what this looks in practice. If you have a variational form for the Poisson problem, just the simplest possible problem, and if you write down the stiffness matrix, the ij entry is just the gradient phi, gradient vj, the two basis functions, the and j basis function. You write it as a sum of the elements. You apply a quadrature rule. When you factor things together, this is B. The degrees of freedom to quadrature points is the evaluation of the gradient of the basis functions at quadrature points on the reference element. For the same geometry, the same order, this is one matrix. Okay? This happens on the reference element. And this is all of D. The Jacobians, if you have a coefficient here, you will evaluate it here too. Everything else, most of the computations actually are done in the most embarrassingly parallel part. This B you don't want to, you can further optimize by not applying this B as a matrix, but using tensor contractions, you factorize it on, in the situations where both the degrees of freedom and the quadrature points have tensor product structure, on quadrilateral and hexahedral meshes, for examples. So when you apply B, instead of having one big sum, you have a nested sum, and this reduces the flops and the memory transfer significantly. So you're not fully optimal. You're off P per degree of freedom in terms of flops, but that's very acceptable. All right, and this was the foundation for a set of benchmarks that we developed under SIT. We call them the bake-off problems, these affectionately BPs, that we used to compare different finite element codes, and this is kind of standard for the community. BP1 is applying a lot of iterations with the mass matrix. So NEC 5000, MFEM, and DO2 are three harder codes that we compared. These are all the same plots where we have problem size versus throughput. Throughput inversely proportional to time, so higher better. Different curves with different orders. As you can see, for the same number of degrees of freedom, higher order is significantly better. Sometimes, times better, 2 or 3 times better. You can also see here that DO2 was killing us the first time we did that. We wrote a paper on this, and one of the fun things about this was that we learned from each other. So this is the updated example. I mean, we kind of looked at this and we're like, oh, what is going on here? They must have vectorized over the elements. So we also vectorized over the elements, and I like benchmarks like this because they lift all the boats, and it's fun to know how good you can do and if you're missing something. So yeah, we have a paper on that. Now for MFEM this was still CPU results, but to push these results to GPUs, we had to do a lot of work, and without the ECP, I don't know if we would have done it so readily. We basically had to refactor the whole code to expose kernels in a very simple way, taking all this advanced object-oriented C++ and dumbing it down as much as possible to pure C objects, and showing for each of the arguments to these hot kernels, what is the input, what is the output, what is read-write. This is critical if you want to minimize, if you want to manage the memory spaces between the CPU and the GPU well. So this was tons of work. But once we did that, now we can target a variety of backends. We have these kernels that we can capture as lambda functions. We also can call libseed, this optimized library that I mentioned. We can call other things like Oka that has just-in-time compilation. Or we can directly go to CUDA heap and now also SYCL. And so similar to these bake-off problems, now this is GPU results with MFEM. This is BP3, which is kind of like a diffusion problem. And the difference between first and I think it's 6th order here is very dramatic. For the same degrees of freedom, you get much better performance. Going from 1 to 4 GPU, the performance falls a little bit. I mean, here we're about 2.5 gigadovs, billions of degrees of freedom per second. But from 4 to 1024 GPUs, there's almost no degradation in performance. And here we are solving 2.1 teradovs per second. This is the 34 billion size problem in a matter of minutes. Okay, so this was on V100. I want to say that the kernels that we're developing, of course, performance portable. This is a V100 versus MI100. Another important thing is that how far to the left we are on this graph, how many degrees of freedom do we need to get a decent performance? As you can see, this is in the tens of millions here. That's a lot. We want to be much less. That's one of the things about GPUs. You need to feed them. And these are some new kernels where we can actually reduce to hundreds of thousands of degrees of freedom per GPU and still get good performance. And we also can take advantage of tensor cores on some of the NVIDIA hardware. Oh, I don't have the MI250X results, but they're on one of the SID reports. All right, so we talked about meshing. We talked about performance and harder methods. I want to briefly touch on solvers and preconditioners. So I already mentioned AMG for scalar diffusion for H1 problems. Another a little bit more complicated problem is electromagnetic diffusion. So this is in the space H curl where you have tangentially continuous vector fields. And it's a Maxwell problem, second order Maxwell problem, which is definite, positive definite. So this coefficient beta here is positive. Okay, so it's kind of in the time domain, it's a diffusion, electromagnetic diffusion. So a while ago, we kind of solved this problem. We found a really nice way to solve it using the so-called Hip-Marshall decomposition. That is a statement about the structure of this H-curl finite element space called the Nedelec space. And basically what that decomposition says is that any function in the space is a gradient of a nodal field plus direct interpolation of a vector nodal field, this pi operator. So this just interpolates, it's not a projection, it's an interpolation in the Nedelec degrees of freedom. And whatever is left here is small. Small enough that you can handle it by smoothing. And so based on this, you can develop a solver in its additive form. You just do a subspace correction in the space defined by G, another subspace correction in the space defined by pi, and just smoothing for this guy. This is an auxiliary space preconditioner. And in these two subspaces, the variationally restricted operator, so if this is the matrix A, in this case, if you plug the gradient here, you just get beta gradient U gradient V. So this is pure Laplacian. And this is something like elasticity, like a Kapok Laplacian. So these are problems nodal problems that existing H1 AMG methods can handle well. And so this solver is called AMS. This has been used now for a long time. It scales really great. It really kills this problem. But only low order. This was all first order. So how do we take this now and apply it to these operators where we don't have matrices anymore? We don't want to assemble the full thing. And they're all high order. That has been another major effort for us in the SID project and generally on the MFEM team. And people call it matrix-free preconditioning. It's not completely matrix-free, you will see. I prefer to call it preconditioning of partially assembled operators. So this just reiterates that if we have order P method on a quadrilateral, you have P plus 1 times P plus 1 degrees of freedom of P to the D in general asymptotically, you do not want to assemble the matrix. And this is the standard set by the MATVEC, by the operator evaluation. You want O of P to the D memory transfers, so optimal, O of 1 per degree of freedom. And you want O of P to D plus 1 computation, so O of P per degree of freedom, nearly optimal. You want optimal transfer and nearly optimal computations. If you go above that, then your solver all of a sudden has become much, much more expensive than the MATVEC. Okay. So again, very active area of research, and there are many, many papers in this area. Now, here's our approach. It's based on this idea of low order refined. And the idea is to simply take these degrees of freedom, which are now all connected in this element, and connect them with linear edges and interpret this as a macro element that is on a lower order mesh. Okay? So this is what's happening here. You have big curved hard elements with a varying hard field that is represented here and mapped to a refinement, low order refinement of this mesh, and piecewise constants instead of this continuous field. Okay? Now it turns out that if you define a proper basis, a proper higher order basis, which is not for H1, for nodal degrees of freedom, this was well known, but for the other spaces, for H curl and H div, this was not known until recently. If you define the proper basis, your mass and derivative operators, so mass and stiffness matrices, will be spectral equivalent on these two meshes. And this holds for H curl, H div, and L2, including some digit discretizations for diffusion. And so the idea is you don't assemble the operator here, you do just matrix free, just what we discussed. But for preconditioning, you assemble a sparse matrix here, you define a preconditioner for this one, and use it directly as a preconditioner for the matrix reaction of the operator on the harder mesh. So you reduce the problem that you don't know how to solve to a problem that you already know. So any improvements in lower order preconditioners can directly be taken advantage of. So as I said, for H1 this was well known, but for H curl it was not. And this is what we do here. We're using this AMS algorithm on this mesh directly with this transfer. And this is what we call LOR. LOR is low order refined, this approach, AMS. And this is significantly faster, orders of magnitude faster in the assembly compared to using the matrix-based version, which is the only other option we had in the past. And that's because the number of degrees, the number of non-zeros is 2 orders of magnitude less. Again, it boils down to memory transfer. This also works for HDiff. This is, for example, flux-based radiation diffusion. And the solver there is called ADS. But again, the point is we're just reusing existing preconditioners for lower the sparse matrices to precondition matrix-free harder operators. For HDiff, it's not as great. We have a better solver for that. But this is just this is a very nice very natural correspondence between these harder and lower order refined spaces. And we have a paper on this. This is work with Will Pasner and Clark Dorman. I will say that this lower order refined idea is actually useful for many other things. One of the things that it is very useful for is connecting. So I've been talking about high order. We're very excited about high order. Not everybody is super excited about high order. There's a lot of codes that are not high order yet. Well, you can connect higher and lower order refined and lower order codes with this lower order refined idea. So you don't just map higher order values to lower order values. You need to map them to the lower order refined values. So there needs to be enough refinement here, enough information that you can recover things. So this space needs to be fine enough. But with proper interpolation and restructure operators, you can prove that you can actually retain accuracy. And you can also retain conservation and recover functions. All right. So that's, maybe I'm a little early, actually. I don't know. That's most of what I wanted to cover today. So there's a lot of, this work is, you can find more information on all the papers on our websites. A lot of this is open source software, actually almost everything. MFEM and SEED, the two main projects. MFEM is the finite element library, and SEED is all the Exascale work. Some of the things we're working on are continuing to work on algorithms that are motivated by the GPU hardware. I think we will see more and more of that because that really changes the map behind what we need to do. For example, matrix-free preconditioning. Automatic differentiation, design optimization, I hinted at that. This representation, decomposed representation of hardware operators allows us more control, in particular, allows us to differentiate very complex codes and use them as a component instead of a surrogate models, use the actual codes when we do optimization. And we're looking at other physics and spreading the hardware virus to everything. And coupling, the multiphysics coupling in an accurate and conservative way. And that's what I mostly prepared today. I want to put this slide again. If you want to give some of this a try, hands-on, tomorrow morning you can sign up here and we'll do this on Amazon Cloud. All right, that's it.